Hello, everyone. I'm Siddhartha Jayanti from MIT, and I'll be telling you about our paper, Atomic Fast Arrays, which is joint work with my advisor, Professor Julian Chung. What is the array object? It's a data object that supports three operations. The constructor, initialize m, f, creates an array of m elements, also called locations or components, which are indexed from 0 to m-1. The ith element's value is initialized to f of I. Here, f can be any simple function that takes constant space to store and constant time to compute. A common choice is f of I is equal to 0 for all indices I. The other two operations are the standard read and write. Read I returns the value of element I, and write I, v updates the value of the ith element to v. Let's see a quick example. Initialize phi, I square creates an array of length 5. Writing -5 to the third element does the following. And now read 4 returns 16, and read 3 returns the newly written -5. The standard implementation of an array allocates a block of memory sufficient to store m elements, initializes all the elements via a for loop, and uses the architecture's native load and store operations for read and write. Thus, the space complexity is O of m. Initialization takes O of m time, and read and write operations take constant time. Are these asymptotic complexities optimal? Or can we do better? That is the motivating question behind our line of research. Perhaps surprisingly, we can indeed do better. If we sustain a constant factor overhead in the runtimes of read and write, we can tremendously speed up initialization. In fact, we can bring the initialization time complexity all the way down to a constant. Accordingly, we call an array implementation fast if all three operations, initialize, read, and write, take only constant time. We can even achieve these time complexities with only a constant factor blowup in space. Single process fast array algorithms have been in the literature for several decades. In fact, the so-called folklore algorithm for the problem was given as an exercise in the celebrated Hopcroft and Ullman text in the 70s. The folklore algorithm uses 3m plus O of 1 words of memory to store an array of length m. A significant direction of research in the last decade has focused on cutting down this constant factor of 3 in the space requirement. In 2012, Navarro showed that compression techniques could be used to reduce the space complexity to m plus little o of m. And a series of results by several research groups in 2017 devised bit packing and chaining techniques that reduce the space complexity to m plus O of 1. The work of Hagerup and Kamer further shows that this space complexity is the best possible. In recent empirical study, Fredrickson and Kilpinane implemented the folklore algorithm and Navarro's algorithms and found that these fast arrays significantly improve runtimes when up to 10% of an array is accessed. Fast arrays have several applications, including constructing adjacency matrices for sparse graphs, including social networks, road networks, and expanders, certain hash tables, and in some complex data structures like Van and de Boas trees. In general, any algorithm that has a greater space complexity than time complexity, not counting initialization, can benefit from fast arrays. To the best of our knowledge, all previous work on fast arrays has been in the sequential model, that is, for single processors. In this paper, we, for the first time, introduced concurrent fast arrays. In our model, once a process initializes a new fast array in constant time, all P processes in the shared memory system can concurrently do operations on that array. Our algorithms are designed for architectures in which it takes constant time to allocate a block of memory, think malloc and C. In our experiments, we verify that standard multiprocessors do indeed have this property. We assume that all the values in an allocated block of memory will initially hold arbitrary garbage values. Furthermore, we assume support for the compare and swap, CAS instruction. Our goal, in turn, is to design fast arrays that are linearizable and weight-free. By linearizable, we mean that each operation by a process PI, which actually executes over an interval of time, appears to take place instantaneously at some point between its invocation and return. Weight freedom means that each operation by a process PI completes in a bounded number of PI's own steps. The main contributions of this paper are threefold. First, we designed a linearizable weight-free concurrent fast array that supports initialized read and write in just constant time, requires only O of m plus p space to support a single array of length m for p processes. Furthermore, if multiple arrays are initialized, we show how to restrict the space usage to be a mere big O of big M plus p, where big M is the sum of the lengths of all the initialized arrays. Second, we implement our algorithm and chart the empirical runtimes of the three operations. Finally, as I'll describe in more detail at the end of the talk, we enhance our algorithm to one that supports constant time read, modify, write, RMW operations such as compare and swap, fetch and add, etc., along with read and write. In the remainder of the talk, I'll develop our algorithm, explain our experimental findings, and touch on the enhancement to a more generalized fast array. I'll now describe our algorithm and develop it starting from the ideas of the folklore algorithm for a single process. To initialize a single fast array data structure of length m, initialized to f of I, we simply do three things. First, we store the initialization function f. Second, we allocate three arrays, A, B, and C, all of length m. And third, we allocate a counter x and initialize it to 0. The allocated arrays initially hold arbitrary values. However, rather than display them and clutter the slides, we simply use the gray background to symbolize that an array element still holds its initial arbitrary garbage value. We will use white backgrounds for elements that the algorithm has written values into. We call such values valid. Here, A is called the principal array, since it stores the current value of all elements that are written to after the array is initialized. For example, if write 3, -5 is executed, then our algorithm writes the value -5 into A3. In our diagram, we have illustrated that A3 is valid by giving it the white background. But how will our algorithmic representation remember that A3 does not hold an initial garbage value like the other elements of A? To remember this, we use the certificate array C. In particular, we write down the index number 3 in the next available entry of C, in this case C0, to recall that A3 holds a valid value. Therefore, we call C0 a certificate for index 3, since it certifies that A3 is valid. But how do we distinguish that the first element of C holds a valid certificate as opposed to the rest of the elements of C which hold garbage certificates? This is precisely the use of the counter x. The convention is that C0 through x minus 1 are valid certificates, and Cx is the next available certificate for use. We visually mark the barrier between the valid and invalid certificates in C using the green line. Since we have just added a valid certificate, we increment x. While C0 through x minus 1 stores pointers to all the valid elements of the principal array A, a read I operation would need to quickly figure out whether the element I has a valid certificate without looping through X certificates. The B array of certificate pointers is there for exactly this reason. Right after we write a certificate for index 3 in C0, we store the index of the certificate 0 in B3 so we can quickly locate that certificate in the future. Here is an illustration of the state after 2 more writes, write 1, 17 and write 4, 56 have been executed. In summary, initialize allocates the 3 arrays, stores the function f, and sets the counter x to 0. Read I checks if element AI is valid and returns it if so. Otherwise, it returns the initial value of element I from the stored function f. Finally, write I, v first writes the value v to element AI and subsequently certifies index I if it is not already certified as valid. The correctness of the algorithm follows from the pithy invariant that AI is valid if and only if BI stores a pointer to a valid certificate that is, bi is between 0 and x minus 1, and the certificate at index bi indeed certifies that ai is valid, that is, c of b of I is equal to I. The algorithm we've discussed until now works for a single process. What happens when we bring in more processes? Well, the sequential algorithm is built on two structures: the simple principal array and the certification mechanism consisting of B, C, and X. The principal array is easy to maintain concurrently, but the real workhorse of the algorithm is the certification mechanism. And maintaining the proposed structure poses some problems in the face of concurrency. In particular, if different processes try to certify different indices concurrently, there would be linear contention at the counter X, and all the processes would want to grab the next available certificate C of X. This linear contention would translate to at least a linear blowup in the time required to certify a new index in the worst case, if dealt with naively. Our algorithm introduces several new ideas to avoid this blowup in time complexity while still using only linear space. Our first idea is to dissipate the contention on X and C by simply maintaining several certificate arrays and counters, one for each process. In our illustration and examples, we'll focus on the case of just two processes. The idea is generalized naturally to any number of processes P. If AI is first written to by process 1, then its certificate will be in the subarray C1, 0 through X1 minus 1. And if it is first written to by process 2, then its certificate will be in the valid portion of the array C2. Correspondingly, the certificate pointer array B will store certificate array comma index pairs of which array and which location in that array holds the valid certificate. This solution works, but it blows up the space complexity to m times p. Since every process should have enough certificates to certify all the indices in case that process is the first to write into every one of the elements of A. To overcome this space complexity hurdle, we introduce array doubling. With array doubling, each process PI can start with a constant sized array certificate array CI and only expand its array to a larger size if it needs to certify more elements. Thus, the sum of the lengths of the certificate arrays of all processes to certify each of the m indices once is O of m plus p. It seems our space complexity problem is fixed. Alas, things are not that simple. Consider the following run with concurrent writes. We consider a run where both P1 and P2 write 1 into the second location. First, they each write 1 into A2. Subsequently, each of the processes notices that A2 is not certified and goes on to certify the element. That is, they each write a certificate in their certificate arrays and increment their counters. And finally, P1 writes a pointer to its certificate in B2 to finish its certification. And P2 overwrites the location with a pointer to its certificate. The run is indeed linearizable and thus correct. However, both of the processes have used a certificate to certify the same index. In the worst case, all P processes could do this at all M locations, and the space complexity, even with array doubling, would be omega of M times P. So we are still left having to reduce the space complexity. The space complexity issue occurred when P1 and P2 both certified A2. However, we can make a clever observation. As soon as P1 wrote its certificate pointer in B2, A2 was certified. So if P2 had realized that P1 had already written a valid certificate pointer in B2, it could have simply walked back its attempt to recertify the location with its certificate rather than overwrite the old certificate pointer. In particular, we introduced a synchronize and walk back scheme. In order to synchronize, we replaced the writes to B2 with cas operations. Since P1 acts first, its cast succeeds and certifies index 2. However, when P2 subsequently attempts its cast, it will fail since the value of B2 was changed by P1. So it casts and fails. Therefore, P2 can now walk back by decrementing x2. This walked back certificate can be reused at a later time when P2 needs to certify some other location. Since locations are now only certified by a single process, we get the desired time and space complexities, right? Well, not quite. It turns out that we can run into a nasty race condition if we're not careful in our implementation of walkback. We now illustrate this potential race condition by giving an example run. For concreteness, let us fix the initial function f to set all elements to 0. Recall that the elements with gray backgrounds have arbitrary, potentially adversarial values in them. The race condition that we are interested in requires the garbage value in B2 to be C2, 1. That is, a pointer to P2's next available certificate. Now, we once again consider what happens when processes P1 and P2 write 1 to element 2. After each writing 1 into A2, they each write a certificate in their next available location and increment their counters. The race condition will result from an interesting pathology associated with the current state. Notice that while neither process has attempted to cast a certificate pointer into B2 yet, element A2 is already certified, since B2 happens to point to the valid certificate that P2 just wrote. At this point, process P3 reads location 2. P3 reads B2. X2 and C2, 1. Notices that A2 is valid and thus reads and returns the value 1. Now let's extend the run and see what can happen if P3 reads location 2 again. Once again, P3 starts to check whether A2 is certified by reading B2. But before it can go any further, it stalls. Let us remember that P3 was about to check the validity of the certificate pointer C2, 1. Now, P3 stalls, and P1 and P2 finish executing their certifications in the same way we had seen before. That is, P1 casts its certificate pointer successfully, and P2 fails its cast and walks back. Now, when P3 checks the validity of the certificate pointer C2, 1, it reads that X2, and because of the walkback, the previously valid certificate is no longer valid. Thereby, it computes f of 2 instead of reading A2 and returns the value 0. The actual value of element 2 was initially 0 and became 1. However, P3 read it to be 1 and then 0. This run is thereby not linearizable. While this race condition is tricky to find, once we've found it, it's easy to remedy. We recall that the main cause of the race was the pathology that the initial garbage value of B2 happened to be a pointer to the certificate that P2 would use to write and certify the index 2. In order to avoid that race condition, P2 simply checks whether the initial value of B2 is a pointer to its current certificate by reading X2. And if that is the case, it writes a tombstone null value in this location, which won't be treated by any process as a real value. And it increments its counter past this certificate, so it can use a new certificate that avoids this problem. Incidentally, in this case, P2 would also need to array double before it has a free certificate. Since B is an array of length m, there are at most m initial values in that array that will lead to tombstones. So the number of tombstoned certificates is bounded by m. Finally, we have achieved our space complexity of O of m plus p. Working out the details and properly implementing array doubling to give worst case rather than amortized constant time guarantees leads to our concurrent fast array algorithm on the right. To ensure that there are no more lingering tricky race conditions like the one I just presented, we identified the main invariant of our algorithm and proved by induction that our algorithm is indeed linearizable. I've described our concurrent fast array algorithm until now. By definition, such a fast array supports only two operations after initialization, read and write. However, hardware arrays in modern multiprocessors are generalized. That is, they support more primitive operations. For example, cast, fetch and store, and fetch and add are common examples of such operations. These operations are widely used in concurrent algorithms. In fact, they're even absolutely necessary for some applications, such as building weight-free data structures. Due to the indispensability of these RMW operations, we define a generalized array to be an array that supports not just one, but indeed every RMW operation offered by the underlying architecture. A key contribution of our paper enhances our concurrent fast array algorithm that we just saw into a concurrent fast generalized array algorithm. Unfortunately, I don't have time to detail the transformation in this talk, but the full algorithm is developed in the paper using a technique that we call fusing. The summary of our algorithmic contributions is the following. We introduced the concurrent fast array and generalized array problems and designed a fast generalized array that supports all RMW primitives supported by the architecture, takes only constant time for initialization, read, write, and any of the RMW operations, requires only O of m plus p space for a single array of length m, and requires only O of big M plus p space if multiple arrays of combined length, big M, are initialized. We achieved this algorithm through the introduction of 6 ideas. I described the first 4 ideas for designing a concurrent fast array in this presentation. The remaining 2 ideas are described fully in the paper. Having described the algorithmic results, let me now briefly comment on the experimental runtimes of our fast array algorithm. We coded the algorithm in C++ and ran experiments on a machine with 2 8-core Intel Xenon CPUs with 2-way hyperthreading. In our first experiment, we timed, in seconds, how long it takes to initialize an array to all zeros for various lengths of array. The x-axis is array length, while the y-axis is the initialization time measured in seconds. The blue line represents a standard implementation for an array that uses C's specialized memset initialization function that is optimized to beat out initializing by a for loop by an order of magnitude. The red line is our concurrent fast array algorithm. We see from the experiment that our initialization algorithm indeed takes constant time regardless of the length of the array being initialized. Furthermore, our initialization is about 10,000 times faster than memset for initializing a 1 GB array. Next, we measured the runtime per write. Once again, the blue line is the baseline set by the standard implementation. the speed of a fast array write depends drastically on whether the location being written to is already valid. Thus, we chart the speed of writes to locations that are invalid, i.e. the first time an element is written to, in red, and the speed of writes to locations that are valid in yellow. Our experiments show that while the first write to a location can take 6 to 21 times as long as a standard write operation, all subsequent writes are much faster, taking only 2 to 5 times as long as a write to a hardware array. In our final experiment, we measure the time per read. Once again, the blue line is the baseline set by the standard implementation. Since the speed of a fast array read can depend on whether or not the location being read is valid, we measured the speed of each type of read and report them as the yellow and red lines respectively. Interestingly, our experiments suggest that the speeds of the two different types of reads are similar, and that fast array reads are only 2 to 4 times slower than reads on hardware arrays. In this work, we introduced the concurrent fast array and fast generalized array problems. Further, we designed algorithms for each of the problems, proved their correctness rigorously, and implemented fast arrays to show that these arrays can actually be efficient in practice. In the future, we look to use fast arrays in the design of other data structures and algorithms, such as hash tables. Thank you very much for your attention.